Can we start the session? Right? I think you are ready for that. Okay. So
एक सेकंड
Okay, sorry for interruption and delay. My connection was lost meanwhile, so I was not able to connect. Okay, so let's start with this session. I think it's audible and visible too, right?
Yes, sir.
Yes, sir.
Yes, sir.
Uh, okay, so last time what we have covered so far. Is it visible? The screen is visible. Blank screen is.
Yes,
Yes,
sir.
sir. Visible.
Okay. So last time we have discussed about the signal and the system, right? So what is a signal and system does compose of two words, so signal and system. Then we have discussed that signal is a collection of data and the system is a entities which process the data to produce some desired outcome. So this part we have already covered, and then we have even discussed about the syllabus and structure of the syllabus that we have discussed 5 chapters that you have to learn within the span of this course, and within the out of these 5 chapters, the few chapters are basically address the types of signals and systems, and other chapters are involved the processing on the signal and system, right? It includes the Fourier series, Fourier transform, Laplace transformation, Z transform, and finally, whenever we have a signal in analog form and we want to convert the signal in digital form, so we need to sample the signal. So then the last chapter is dedicated to the sampling and reconstruction of the signal. Out of this, the sampling is basically performed at a transmitter side and reconstruction is basically performed at the receiver side. Sampling is a process to convert the continuous time signal into discrete time signal, and reconstruction is a process to convert back from discrete time signal to the continuous time signal. Then we have even gone through some reference book including the Signal and System by Anand Kumar, Alan V. Oppenheim, and all. And I have suggested the two main book as your reference book. The first, which is widely adopted in all over the community, even if you learn the same subjects in some Oxford University or some best university of the world, so they are even following the second book, Signal and System, written by Oppenheim. Right. So this is the book that that I prefer first as a first reference book, and the second this most of the theoretical fundamental and foundations have been laid down on this book. Now secondly, I will suggest the another book which is written by the Anand Kumar, which is full of the examples, which is there are lots of examples, and whatever the examples are given as unsold example in most of the books, in this book, the first book Anand Kumar, this examples have given in soul form, so you will have a better idea. So from example point of view and to consider for assignment and tutorial submissions, this first book will be very useful, and that is written by the Indian author Anand Kumar, and both the books are available in under the Printise Hall publication, right? So these are the things. Initially, this subject you have a 4 lecture. One lecture will be it has been designed that the one lecture will be delivered by the principal sir, and the 3 lectures will be delivered by myself. But due to the unavailability of the principal sir, it has been now finalized that all the 3 lectures, the one lecture will be dropped out from your timetable, and the remaining 3 lectures of these subjects will be carried out by me throughout the semester. And now hopefully we will meet again physically in February, because I hope as the vaccination news is around, all the vaccine will be planned out by the government to give in January for most of the people. So if the 20 to 25% vaccination will be given, so most of the people are safe, because the carrier the conduction of this virus will be reduced. And then in a February, that with if we think about from a press outlook, that we can tell that in February we can have a physical meeting, and most of the classes will be start. That is just a prediction, but I think in February we can have a physical meeting in a laboratory sessions as well as in a classroom. Okay, so you may have a better idea from this one. But now, before that one, Here I'm going to start with some basic fundamental concepts today of a signal and systems, and this is the first lecture you may consider. The earlier lecture you may consider is about to discuss about the laboratory sessions and especially discuss about your reference book and syllabus structure. Now from today we are going to start the first lecture of a signal and systems, right? Yesterday I was busy with a meeting, so I'm not able to take your lecture, but this lectures we will arrange somehow in a future, right? In some days when you and me both are free, so I will arrange this lecture. So now here we are going to start the first lecture of this date, right? And in the first lecture we learn about the basic signals, right? Very basic signals, and these are the signals that we are going to cover in this lectures. They are widely used in most of the applications of a signal and systems, and they are even for a further analysis the signals are even very useful, right? So this basic signals that we are going to learn over here, the first signals that we will learn is the impulse signal. This is known as a impulse signal, right? Then the second signal we will learn in the same lecture will be a unit step signal. Then in the same line, we can have a learn about the ramp signal. Sine or cosine signal we will learn next to that. That is known as a sinusoidal signal. We will learn about how to represent the signal in mathematical form, and how basically the signals are useful to for a analysis point of view, and to carry out the something in the future. So how to represent the signal in mathematical form and application of the signals in a signal and system subject. So that we will learn later on regarding the exponential signal. One more signals that is very useful, which indicate the sign of signal. If you want to change the sign of signal, so we will generally multiply with the signal, and that is known as a signum signal. It is known as a sign signal also. And then we will finally discuss about a very important signal, sync signal. Yeah, one more that we will learn is the Gaussian signal, right? So all these signals we will basically learn in the course of this subject. So before we are going to start with the signal, that we need how to represent the signal. So we will go one by one. We will address we will discuss about the applications of signal and mathematical representation of signal one by one, starting from impulse signal, and we ended over at the Gaussian signal. So these are the 8 basic signals that you should know how to deal with that signal, and you should have a clear idea and pictures about those signals. So I just make those things very clear in the first one or two lecture, and starting from a impulse signal. But before to this, we should know about how to representation of signal. So before we start with the impulse signal, that we first learn about the representation of signal, how to represent the signal, right? So any signal is basically made, or it has been constructed with the variable multiple variables, right? But here we maybe a two-dimension signals is have a two parameters, three-dimensional signal has a three parameters, etc. But now in this sessions, especially we are limited with only two-dimensional signals, or the signals which has only two parameters. So the signal is basically represented by the amplitude versus time, and not necessary we can have a different scenario also, but for the understanding point of view, we'll start with the signals which has only the two parameters. One is amplitude and another is a time, and generally the amplitude is presented on a y-axis and the time is presented on a x-axis, right? So we can start with this one, and then later on we will deal with the various kind of a signals. So whenever we have to represent the signal, like any of the signals, so basically it comes in a two category. One is known as a continuous time signal. Uh, these are the signal in which it basically vary. Its amplitude does vary continuously with a time, right? If I have to write anything about this one, we can say the amplitude is continuously vary with time, right? So this is known as a continuous time signal. The simple example of this sinusoidal signal over here, that you can say every time instant, if I pick up any time instant over here, I can find one amplitude, right? If I pick up one time instant over here, then I have different amplitude. And if between time t1 and t2, there may be also I can take the infinite number of samples. So this is known as a continuous time signal. It is known as a continuous time signal because for every time interval, we can have a different amplitudes. So if I can divide this time interval, the total time interval, in infinite number of samples, or I can divide the this period, t period, in an infinite time interval. So for every interval, I can have an individual input, right? So that's why it is known as a continuous time signal. And most of the signals that we are recorded by the sensors and all, they will provide us a continuous time signal, right? Okay. Now the how to represent this signal? So this signal is generally defined by the function g of t. If the signal is considered as a g of t, so I can say g of t is has some maximum amplitude as a, and the negative peak amplitude is a minus a. So we can say this is a symmetrical signal with the peak amplitude a, and the shape is sinusoidal. This is a simple example, and you came across such kind of a signals earlier also. So that shows this a shows the amplitude, right? And wc shows the frequency in radians. So that shows the frequency. But if you observe this waveform, that we can say this amplitude and frequency are fixed, they are constant. Once it is defined, then it remains a fixed, right? So the time is only the parameters which does vary, and is the time does vary, then amplitude of the signal does vary. So this u of t is actually known as a function of time, right? This is a function of time, but this g of t is basically defines the amplitude of signal. It's just to define amplitude of signal, and this amplitude is a function of time. So if the time does vary, different value of time, if you put in this equation, so we will find the different value of amplitude of this signal. So this amplitude is a function of time. If time does vary, then amplitude does also vary. So in such kind of a signals, we can have a one function, and by this function we define the signal. So it's a mathematical presentation of the signal. Okay, and here we can say if you want to find any interval t0, if at any interval t0 we want to find the amplitude, we simply put this value of, we insert this value of t0 in this equation, replace the t with that value t0, and if the amplitude a, this is what is known as a fixed value, that is known, this is peak value, peak amplitude of your signal. If this one is known and the frequency does known, then for any interval, time interval t0, we can find the amplitude of the signal by using these equations. So this is the one part. Now if any signal, if it is a discrete time signal, right? So if we talk about any discrete time signal, then discrete time signal is basically differ in the sense that its amplitude doesn't vary continuously over the time, right? It has some discrete time interval like this one. This one, let's say there is one discrete time interval, another discrete time interval like this one, and for every discrete time interval we can have a discrete amplitude, right? So this one is known as a discrete amplitude, and for every discrete time interval we can have a discrete amplitude. So how we represent this one? So let's say this is the 0 time interval, this is the ts time interval, this is 2 ts time interval, and all this, right? In this way we can define. So this ts time interval is known as a sampling interval, where we are taking the sample. This is known as a sampling interval. And the total time interval to complete the one cycle, that is known as a capital T. So we consider this is a uniform sampling. So every TS time interval is same. So if I measure the difference between TS and 2 TS, so that is a TS. And if I measure the distance between 2 TS and 3 TS, so that is also TS. It means that TS is uniform. If you pick up any two sampling, if two samples in a signal, the difference in a time domain between the two samples are always same. That is a TS time period. So TS is known as a sampling interval. That is remains a constant. So the amplitude of this signal at zero time, how we define this? So this one is defined as this amplitude is defined as a zero, a function of g. So g is a function and the value is defined as a zero time. So this can be defined as a g of zero. So what does mean g of zero? It means the value of g of t signal at time t is equal to 0. This is the at time t is equal to 0. We have to consider like this. So if I pick up any value at this time interval, so it can be defined as a g of 3ts, right? It's a similar way g of 2ts, right? G of ts, right? Right. So in generalize, we can say the amplitude can be defined as g of nts, g of nts. That means the value, this means the value of g of t at any time interval and ts. Now the n should be vary from 0, the first sample, second sample, third sample, etc., right? Okay, so that way we can define the discrete time signal. So discrete time signal can be defined in this way. So if the discrete time signal is basically addition of it's a basically addition of the amplitudes of individual time. So how we represent in mathematically this signal, g of t signal is basically nothing else but it is the addition of all the samples starting from 0 to some value of n. N may be infinity also, right? N may be any value, but it is the summation of all the, I mean, you can say how you define this g of t signal in this case. So we can say our g of t signal is the addition of the g signal with the samples are taken t is equal to 0 plus the addition of the samples taken at ts time period plus addition samples are taken at 2ts time period up to, if there are we are taking n number of samples, n may be any values, so we can write the signals is addition of all this, right? Okay, so we can write the g of t signal can be constructed as a addition of all the samples starting from 0 to some value capital N g of t minus nts. This is the means the signal g of t is delay. This is the signal g of t and it is delay by some sample and ts, right? We can have to write here it's n minus ts, it's a t minus ts, we can write like this. Sorry, ts means at ts time, t minus ts means the signal which is originally present, it is delay by some time interval and then we are taking the sample, so that is better. We can write t minus 2ts and then we can define here t minus nts, right? T minus nts. So this is the mathematical presentation of discrete time signal. So now we can see the difference between continuous time signal and discrete time signal. Continuous time signal has an infinite number of samples and every value of samples we have an individual value of or a distinct value of an amplitude, right? So we can be represented in the form of a mathematical equations. But if we talk about the discrete time signal, so in a discrete time signal, the time domain is discretized, right? So we don't have a continuous time signal and we amplitudes are measured at all those discrete time intervals. Amplitudes are measured at those all discrete time intervals. So every discrete time intervals we have a different amplitude. So it can be represented in the equations which is written over here in equation number 1, right? Okay, now we talk to the next part is the basics. We can start with impulse signals, and we will discuss about various kind of signals and how we can represent mathematically, right? So this is a simple graphical or mathematical presentation of continuous time signal and as well as discrete time signal. And in this subject, you have to came across both the kind of signals one by one, discrete time signal and continuous time signal. And whatever the properties of signal and systems that we are going to learn in the next few lectures, that is basically applied to both discrete time signal as well as the continuous time signal, right? So whatever the properties are there that we are going to learn, they with some modifications we will learn for both the kind of a signal. So first today we are going to learn about the first kind of a signal, very basic, first basic signal, and that is known as a impulse signal, right? This signal is very basic signal, and there are a wide amount of applications of this signal, impulse signal, especially whenever we want to convert any continuous time signal to the discrete time signal. So we have to multiply those signals with this impulse signal, right? And how we represent this signal? So this signal is basically present at only one time interval. This will be present at only one time interval. So if I draw like this way, right? If I draw, this is my x-axis. So this signal is present only here, right? At the time interval t is equal to 0. Right? And what would be the amplitude of the signal? So if amplitude, I will consider what is the width of the signal. So I say if A is defined as the amplitude of the signal, is the just to define the amplitude of the signal, and epsilon is to just to define a width of the signal, right? So this width is very small. This width is very small. We can say this width is approach to 0. Is very small width. And what we talk about the amplitude, if we talk about the amplitude so A is infinite large, so large, right? So we can say A approach to infinity in most of the cases. So if we find the area, if we find the area of impulse, that will be tends to 1. The area of impulse will always tends to 1. Right. So in general way, this equations in applications, we can say this signal is known as an impulse signal, and that is defined by delta of t. So delta of t does present at only one instant. It would be a 1 when t is equal to 0, right? But if somebody will take the sample somewhere here, so the impulse is absent on those other points. So impulse is present only at a single point where t is equal to 0. So we can say this function delta of t would be a 1, it would be a 1 at only t is equal to 0. If you find some other instances, so all other instances, it would be a 0. So it would be 0 otherwise, or other values of t, right? This is very important equations that you need to note down, right? So if you need to note down, this is very important equations. So this is known as a impulse signals, and the response of such kind of a response is also sometimes known as a impulse response. So it is also known as an impulse response. So this impulse signal is will be provide a only it will be present at only one instant, right? That's why whenever somebody becomes a very much angry, and so we can say you got the impulse, right? You becomes impulsive, and sometimes some persons are continuously after a particular period of times it becomes angry, right? Every in a day they are becomes angry, most angry is 10 times or 20 times. So you say you have impulsive nature. So impulsive nature means instantly you are high, at some points you are high, but then you calm down, right? You come back to your original positions. And if somebody becomes angry instantly, you can say you have impulse now. So I am not going to talk with this. So that actually comes from this one. Impulse means you can have some impulse, you can have some very high amplitude at some particular instant of time. But if for other instant of time if you find, so the signal doesn't exist, or the signal does have a zero amplitude. And the very important property of the signals is that if you multiply this signal, if I integrate any of the signal g of t with delta of t, right? If I integrate any signal with this g of t, and this integration limits I put from minus infinity to infinity, right? So it means this shows the multiplication of g of t with impulse response delta of t. So what you expect if you multiply any signal with delta of t? So what does exist? So in most of the cases this a is to be considered in some of the for in some of the cases, rather than to consider it as infinity. In some of the cases, for basic understanding point of view, we are just considering this has some amplitude 1, right? This is very, in some of the text they are using this one is a infinity, but in some texts they are considering the impulse response would be a 1. We have a 1 amplitude. It is impulsive, but it is a 1 amplitude at some time interval. So we will go with this belief, right? We will consider this impulse response is a 1 for the in a particular instant t is equal to 0. So that says if you multiply any signal g of t with delta of t, it gives the value of that signal where the impulse is present. So where the delta of t is present, so delta of t is present at t is equal to 0. So we are getting the value of the signal g of t where the impulse does present. So that is the present at 0 interval. So we can say the value of signal g at a 0 interval. So that can be defined by z of 0. Let's understand this concept with some example, right? Let's say I have a sinusoidal signal. Uh, okay, rather than sinusoidal signal, let's consider I have a cosine signal, right? I have a cosine signal which has some peak amplitude plus 1 here, right? You multiply, or let's say this is a 2. You are we can have a signal with some amplitude 2, or let's make it generalized so I think you have more idea. It's a amplitude a, right? And how you define this is our g of t signal which has a peak amplitude a cos omega 0 t. Omega 0 may be any value, right? Now I multiply this signal with some impulse, and where the impulse does present, so impulse does present here, let's say 0, right? At 0 the impulse does present, it is present here, it is present here, and that is the time interval t is equal to 0. That is known as a delta. And peak amplitude we are considering as a 1. So that has a 1 amplitude. Now, if we multiply both the signals, so what happens at some point here, if we consider T1 point, this is at T1 point, it has some amplitude, right? A1. But now, if you are multiplying point to point, so at this T1 interval, it has some amplitude A1, but this signal doesn't have any amplitude. So it is multiplied with the 0, right? It is multiplied with the 0. The same happens over here also. They have some amplitude as a minus A2, right? But at this point also the impulse response does 0. If we go in a negative direction here, so in negative direction also the same scenario will happens at some minus t1 time, minus t2 time, impulse would be a 0. So how we represent the delta, how we represent the g of t? We can represent the g of t is a continuous function of time, and it has a multiple values, right? Multiple values, minus a1, minus 8, minus a2, minus a1. Then it have a, right? We can consider t is equal to minus 1, t is equal to minus 2, t is equal to 0. It has all these values are there, right? It has a continuous function of time, so it has all this value. But now what we talk about the delta of t, so delta doesn't have all this value. It is present only at t is equal to 0 with the amplitude 1, and it has 0 value all other points. All other point it has a 0 value. So if we find the area, this integration is the just shows the area of g of t of multiplication g of t and delta of t function, right? It is the area of g of t and delta of t. So we can see if you multiply minus a2 with 0, that you turn out with 0, minus a1 with 0, right? If you multiply these two things, that would be a 0, a with 1 a, then you will be a 0 0. So you will find after multiplication of g of t and delta of t, all other points becomes a 0, will remains only the single point at which the impulse does present. So that means what? That means the value of g signal. What is the value of g here? This is the value of signal g of 0, right? At 0 interval, we are finding the amplitude A. So the value of signal g of t at t is equal to 0 would be A. So we can say it left with us only g of 0, right? So we can physically prove this thing. So in a way, we can generalize the formula is that this is not the single case, but for any of the case, if we can say, if we find the area of signal g of t with the impulse response delta of t for any time interval minus infinity to infinity, so it just left with us the value of signal g where the impulse does present, g of 0, right? Okay. Now let's consider the thing slightly different. I means rather than this one, let's consider this is not one here, but it is one somewhere here at a 2, at a t2 is equal to 2, right? It has one over here, and this one can be defined as a delta t minus 2, delta t minus 2, because t minus 2 means it is present at t is equal to 2. So we can write here delta function is 1 at only the shifted point t is equal to 2, and it is 0 elsewhere. So how this one can be modified in this case? So this one can be modified. Now this one is not present here, but this one is present somewhere here, right? Somewhere here t is equal to minus 2. So if you multiply, so what you are getting there, so you are getting this equations is even modified. It's rather than delta of t, we can have a delta of t minus 2, right? So what does it mean? It means the value of signal g where the impulse is present. So impulse is present at t is equal to 0. So it does mean, simple means, the value of that signal where the impulse is present. So that is present at t is equal to 0. So that we can write here this way: g of t value where t is equal to 0. Sorry, t is equal to 2. So that can simply represent as a g of 2. Right. So this is very important property of unit impulse signal will tell us that it is present at only one point, and it doesn't exist at all other points. So if we integrate any of the signal with the impulses, so that gives the value of that signal where the impulse signal does exist. So if the impulse signal does exist at t is equal to t0 times, so it gives a single point value, and the single point value of the function where the impulse does exist, right? I think you understand the concept. Now we talk about the very important thing is the train of impulses, right? There, we have discussed earlier about only single impulse, but if we have multiple such kind of impulses are there, we are not talking about the persons who becomes angry once in a year. We are talking about the persons who becomes angry multiple times in a day. So that is the impulsive nature, we can say impulsive nature, right? So train of impulse comes, so after every some periodic intervals, then he becomes impulsive, and we talk about that kind of a persons, that it's the word comes here is a train of impulses. We train of impulses means we have multiple impulses that are present. So that way we can say for every sampling we can have an impulse at 0 also, right? This is a 1. This at some other interval t is equal to minus ts, we have again impulse does present, t is equal to minus 2 ts, we have a impulse does present, and for every other intervals the impulse does present. In that side, we can say we have an impulse does present is t is equal to ts time, right? Or rather than t equal, I simply write here it's a minus ts minus 2 ts and so forth, and that I simply define as a ts 2 ts and so forth. So you can say for every ts time period we can have a one impulse. So this is known as a train of impulses, the train of a impulses. And as this train is repeated every ts time interval, we can write here this is a function of delta ts of t. This is a function of delta ts of t. And how we can write here? We can write this function delta ts of t is nothing else but it is the addition of all the impulses which are present at a different time intervals, from where it is starting from minus infinity to plus infinity, and that starting from minus infinity to plus infinity, right? Very importantly that we need to consider. So it just tell us that this delta ts of t is just shows the train of impulses starting from minus infinity to infinity. Okay, this is very important. And now one more interesting things that we have to learn about this impulse train is the major application, right? We need to have a major applications of this one, applications. So the major application of this unit impulse is that if we want to convert a continuous time signal to discrete time signal, right? Then this the impulse trains are used. So the major applications here of this unit impulse signal is to convert the continuous time signal that simply we known as a CT, right? That we known as a CT into discrete time signal that is known as a discrete time signal. So if you want to convert any continuous time signal into discrete time signal, that we need the help of this unit impulse signal, right? So take an example of this one. I can draw any signal. Let's say this is my sinusoidal signal. You are very much familiar with the sinusoidal signal, so that I'm giving example of sinusoidal signal most of the time, right? This is the my sinusoidal signal. How you treat this signal? Continuous time signal or discrete time signal? Student, can you reply, please?
Continuous.
Yeah, continuous time signal, right? This is my continuous time signal. Okay, now I want to multiply with some special function so that I can have a discrete time signal, and the sampling interval is ts. All right. So what we can do here, we will multiply this signal with some impulse train, and let's assume this is my some point. This is this any of the point. Uh, okay, you don't consider any of the point, but let's say this is the some impulse trains are present, right? And it may be starting from here. So this is the 0, then we can have a ts, then we can have a 2ts, and that way the train does uh, move, right? So we can have 5ts and 6ts and so, right, and so on. And this is known as a train of impulse. So we are represented, and it repeats at every ts time interval. So we can say delta ts of t. This is the train of impulses. And what is the amplitude? That is 1. So if you multiply with any of the signal, and it is simply multiply with a 1, so it doesn't going to change the amplitude of the signal, because if you multiply any number with 1, that it remains the same. So what does happens over here? At this interval, what is the amplitude of the signal? Maybe a 0 or something nearer to the 0. At ts time interval, what is the amplitude? This is the amplitude of the signal. At this amplitude of the signal here, this is the amplitude. This one is the amplitude of the signal, and this is something here. So we can say this is the g of 0, g of ts, g of 2ts. And in this fashion, if we write all the values at different time interval, 5ts, and this one is simple g of 6ts. So after, if you multiply both the signal over here, and then final output is produced here, then what does it happens? It happens that this one will multiply with only g of 0, that it makes as a g of 0, right? What happens here? G of 0 multiply with 1. Here what happens? G of ts value. G of ts means amplitude of g of t at t is equal to ts time, right? So g of ts value is multiplied with this impulse, which is 1. G of 2ts is multiplied with, so it left with the same value, right? It is all are 1, so that it left with the same value. So after multiplication, if I draw any signal, so this signal will show the same value here, right? Same value. So it is the value of g of 0, right? Similar way, it is the next time it has this value g of ts, then it has g of 2ts, then g of 3ts, g of 4ts, then 5ts, and then finally 6. So you are getting this value like this after multiplication. of this signal, right? This is again, and okay, so this is the way how you represent. So what is the signal? This is g of ts, g of 2ts, g of 3ts, g of 4ts, 5ts, and 6ts. And how you represent this signal? So this signal is simply known as g of t multiplied with delta ts of t. Right. Now you let me know this signal, the last one, is this this is continuous time signal, right? This we can say CT, continuous time signal. Shortly we write CT. And what about this signal? This signal is,
Discrete
yeah,
discrete
discrete time,
signal.
discrete signal or discrete time signal. So if we want to convert any, as per this application, if you want to convert any continuous time signal, if you want to convert any signal which is continuous time signal into discrete time signal, so we need to multiply with the train of impulses. We need to multiply with a train of impulses. So that way we can say this is the major applications of a unit step a unit impulse signal. Okay, and the last 1 or 2 minutes then we conclude this session is, if we take the integration of delta of t, right, then what we are getting? So if you are integrating any delta of t, so it gives us a 1. It means the area of delta of t will give you a 1, right? So if you integrate, and if you integrate any signal if you integrate any unit impulse signal, then you are getting a unit step signal. So that we discuss unit step signal, we'll discuss in a next lecture. But if you integrate any impulse signals, that you are getting a unit step signal. Very interestingly, we have to note down this. Integrating of this one will give us the unit step signal. How it comes, that we will discuss in a next lecture, right? So I summarize the things what we have learned. So that we have learned about the how to represent the signal. So basically we came across the two kind of a signal. One signal is a continuous time signal, is the signal for which the amplitude value is does vary continuously with a time. Then we how we define this, we can define by one mathematical expression of this. And if this function is at a function, this is a function of time, that with different value of time we can have a different value of amplitude of the signal. Then we came across the another kind of a signal, that is known as a discrete time signal. So in discrete time signal we have learned that what we have majorly learned, we have basically learned discrete time signal in which the x-axis is a discrete, it shows a discrete time interval, and amplitude does exist at a discrete time interval. And how we represent this one? So we represent as a g of nts, right? G of nts means the value of that signal, g of t signal, at the time interval nts, where ts defines the sampling time interval, right? And n does vary from 0, 1, 2 up to the some other value of capital N. So that we have generalized the way to represent the discrete time signal, and that is any discrete time signal g of t can be represented as addition of all the amplitudes located at a different sampling interval. So that we can say that is the addition of all the intervals from 0 to capital N, g of t minus nts, right? So we can represent a discrete time signal in this form. So that is a generalized approach, generalized way to represent the signal. And impulse signal, then we discuss about the various kind of signals, and in that category we have started with the first signal is a impulse signal. So impulse signal can be represented by as a delta of t, and which does exist only at a short period of time, very short period of time, and then it vanishes. After this short period of time it doesn't exist, right? It does vanish. And that we define with the, if we can define the amplitude and width. So amplitude is large and width is very small. So generalized way we can define this, delta of t would be 1 for some time interval t is equal to 0, and it is 0 elsewhere, right? Elsewhere it is 0. And the very important property of the impulse signals that we have defined is, if we multiply any of the function g of t with delta of t and we find the area of that multiplication, so that will be turned out with the value of the function where the impulse does exist, or the value of that function at the location of impulse, so if the delta of t is present at zero interval, so it makes a sense value of the signal at a value of the signal g at t is equal to 0 time. So that we have discussed about this one, and with some real time examples we have seen, if the impulse is shifted from other location, so it also shift the value of the signal g of t at that locations where it does actually exist. Then we have defined the impulse, the concepts of a train of impulses, where we have seen, rather than a single impulse, if you have multiple impulses are present, so that is known as a train of impulses. And the train of impulses can be defined as a delta ts of t is as an addition of all the impulses with delta t minus nts. A different nts is defines the location of that impulses, right? And we gone through the major applications of the impulses, that is to convert the continuous time signal into discrete time signal, and where we have taken one example. If you have any signal which is a continuous time in a nature, and if you multiply with the train of impulses, so that it left with us with the discrete time signals which does present at those time interval only. Okay, so that part we have already covered and done. And then at the last session of this lectures we have discussed, if we take the integration of impulse response, so that we're left with a constant value of 1, and that is similar like as a unit step signals. What is the unit step signal, and how we can define mathematically what is the applications of unit step signal, all these stuffs that we are going to discuss in a next lecture. So okay, so Heaven, I now came back to the main screen, but before this I need to take your attendance manually over here, because I am not my laptop is not available with me now, so that I will pronounce your name, right? And you just one by one you have to tell whether you are present or not. Number one is present. One. Yes sir, you have to tell yes sir only. One. Two. Three. Hello, is it audible?
Yes, sir,
Yes,
you're
sir.
audible.
Okay, so
Yes,
three
sir,
number.
you are right.
Okay, so three is absent, right? One, two, three absent. Four. Five.
Present, sir.
Five present. Six. Seven.
E.
Six is present. Seven. Eight. Nine.
Yes, sir.
Nine is present. 10.
Present, sir.
11.
Present, sir.
12.
Present, sir.
13. 13.
Present, sir.
14.
Present, sir.
15. 16. 17.
Present, sir.
17 is present. Okay,
Present,
16.
sir.
Okay, 16 is present. 17 is present. 18.
Present, sir.
19.
Yes, sir.
20. 21.
Yes, sir.
22.
Present, sir.
23.
Present, sir.
24. 25. 26.
Present, sir.
27.
Present, sir.
28.
Yes, sir.
29. 30. 31. 32.
Present, sir.
Present, sir.
31 and 2 both are present, right? 33.
Yes, sir.
34. 35. 36.
Present, sir.
37. 38. 39. 40. 41.
Present, sir. 42. 43. 44. 45. 46. 47. 48. 49. 50. 51. 52. 53. 54. 55. 56. 57. 58. 59. 60. 61. 62. 63. 64. 65. 66. 67. 68. 69. 70. 71. 72. 73. 74. 75. 76. 77. 78. 79. 80. 81. 82. 83. 84. 85. 86. 87. 88. 89. 90. 91. 92. 93. 94. 95. 96. 97. 98. 99. 100. 101. 102. 103. 104. 105. 106. 107. 108. 109. 110. 111. 112. 113. 114. 115. 116. 117. 118. 119. 120. 121. 122. 123. 124. 125. 126. 127. 128. 129. 130. 131. 132. 133. 134. 135. 136. 137. 138. 139. 140. 141. 142. 143. 144. 145. 146. 147. 148.
Present, sir.
43,
Yes, sir.
44, 45, 46,
Present, sir.
47,
Present, sir.
48, 49,
Present, sir.
50,
Present, sir.
51, 52,
Present, sir.
52 present. What is the last number? 53.
Yes, sir.
Okay. 54,
Present, sir.
55,
Present, sir.
56,
Present, sir.
57,
Yes, sir.
58,
Yes, sir.
59,
Yes, sir.
60. Okay. I think this one is the last number, right?
Hello, sir.
Yeah. If anybody is left in this
Hello.
number, yes, yes, yeah. If anybody is left in this number, so you just let me know.
Sir, 15 number has just called me and that
Sir,
his mic
7
is not
present.
working.
Sir, number
Yeah.
6.
Number 6 is not there, right? Okay. So 6 I will add. Okay. Anyone is left?
Sir, 7.
15
7 is
number.
Sir, no.
okay. So I can say the number is who is left here is the 7. Okay. So 6 and 7 number both are there. I just took 6 and 7. Okay. Any other one is left?
Sir,
Sir,
3.
3 number.
Yes, sir.
Okay. 3
Sir,
number.
29.
29. Okay.
sir,
29.
15. 15 number is also left, sir.
1 5. Okay.
Yes, sir. 1 5.
Okay. Okay, so I think it's over and have a nice day and good day. Whatever the things have been covered from here, I think you understand it clearly. And if you have any doubt, you can ask. Otherwise, we will conclude this session. Have a good day. Goodbye to all of you. If you have any questions, you may ask. Right. Okay, so now it's a time to complete the session, and we just you just left the meeting. Okay, have a nice day. Good day.
Thank you, sir.
Thank you, sir.